We're going to prove the normal approximation to the binomial. To set the scene, say that x follows a Poisson with a parameter lambda. Then you know the rule that for large lambda we may approximate x by a normal distribution. Standardizing it, x is a standard normal. And we might improve our approximation using the continuity correction. What is meant by large, I just leave it to your professor or your textbooks because there's different kinds of rules of thumb. So to do the proof, we're going to prove the result. We're going to quite a few results we've used previously about MGFs. Let's state this problem formally. So it's calling here Zn is a Poisson with rate parameter n. So Zn is a sequence of random variables, each with Poisson rate parameter n. We know that the mean of a Poisson is the parameter, same as the variance. Then what the question is saying, show that the standardized version of Zn tends in distribution to the standard normal, i.e. its limiting or asymptotic distribution is standard normal. Okay, so that's the standardized form. Subtract the mean divided by the standard deviation. What we need to show then is we take this MGF of the standardized version of the Poisson and show that it tends to the MGF of a standardized normal, which is this expression. Problem 62, we derive the MGF for a normal, so we can get this result there like that. And then we need another result that was discussed in problem 84, that the convergence of MGFs implies convergence in distribution, subject to the condition about t existing around 0. Okay, so let's do it for this problem. Right, let's use this here to denote the MGF of Yn, the standardized version of the Poisson. Then we substitute for Yn this expression here, which you can see is a linear combination of Zn. Now we use this result here. MGF, suppose we know the MGF for a random variable x, then we're interested in the MGF for a linear combination of x. Then this is the result, connecting the MGF of the transformed x, which we're calling y, to the original MGF for x. Okay, so that takes us to this line here. Now, instead of MGF for Yn, we'll look at MGF of Zn here. We know the MGF for Zn because we're told that Zn is Poisson. Just to kind of make things a bit simpler for presentation, we're just going to call this expression 1, and now we're just going to work on this, which we know is the MGF for a Poisson. Notice, guys, this bit in this expression is that, and this is that. Okay, A, B are constants. Okay, so let's look at this guy here, which we know is a Poisson, but with this variable here, replacing for the old variable, so that's what I've written here in red. And so we have this, okay, which we derived in 67. Okay, now we're interested in taking limits. So basically we want to know what's happening to this expression as n tends to infinity. Well, we know we can rewrite e to that thing like this in red because of this result. Taylor series expansion around 0, or you might call it the Maclaurin series. So I've written this here in red, and I've just taken it to the third order. I'm not going beyond because there's no need. And it's an infinite series, minus 1 at the end. I'm going to tell you why I don't need to write all those on more terms in a moment. We take this expression, let's call it 2, substitute back into expression 1. We have this, and then take n through the brackets. Then what you can see is like this is going to cancel with that. It's going to simplify. You have this is what we want, and then you have all these terms, higher order terms in n, which are written in blue here. Now what you want to do is fix t for any value. We could take t at any real line, and then look at the limit as n tends to infinity, is how we're looking at this. So we're going to have this plus all these blue terms, which are basically getting smaller and smaller. They're tending to 0 as n tends to infinity. So then this will be e to this guy here times e to the some term tending towards 0, so e to the 0 is 1. So we have this, and that's what we needed to show, because that's the MGF for a standard normal. So we can conclude that the limiting or asymptotic distribution of the standardized Poisson is standardized normal. Okay, comment. In more advanced calculus class, you'll see how to deal with these tiny little sums. We can use the big O and little o notation to talk about those small amounts that don't really matter. So if we go back to step 2, instead of writing that line, I could write this. I'm not going to explain it too much, so you've seen big O and little o. I can write this using the big O notation. Then the final line will carry over as follows, and that's the result that way as well. If you want to know more about the big O and little o, you just look up Taylor theorem, big O or little o, and it's explained there.